So we're going to talk a little bit about the one-dimensional kinematic quantities. And this is basically the physics of motion. So we're going to talk about velocity, speed, displacement, acceleration, and we're going to talk about it in one dimension, which means it's going left to right, up, down, very, very simply, so we can focus on what these things really are. Um, Kinematics is the physics of motion. It's how far something travels, which would be distance or displacement, how fast something's moving, which is velocity or speed, how fast something speeds up or slows down, which would be acceleration, and how long any of these things take, which would be time, or sometimes you'll see time interval. And we'll start with displacement. So displacement is the change in position of an object. And a lot of times you're going to be thinking it's distance. But displacement is a little bit more special. It's the actual straight line distance from where you start to where you end. It's also a vector. It's measured in meters, miles, centimeters, anything that you'd measure length in. And symbols pretty much match the situation. You'll see the X, Y, D, and R for radius. So D for distance. X is usually left and right, Y is up and down. And we're going to talk about positive motion or negative motion. Positive is forwards, negative is backwards. Uh, you're moving from left to right, it's positive, right to left, it's negative. And you can assign these things so that they're convenient, which makes it kind of nice. So, as an example, think about a trip that you might take from school to Starbucks because you got to get your coffee, and you map it. Where's the nearest Starbucks? And the mapping program sends you on this nice zigzag pathway, and it turns out that that's going to be your actual trip. And the distance for that trip is 2.3 miles. But if you measured the straight line distance between school and the Starbucks, it's really only 1.4 miles. So the displacement is 1.4 miles, and the distance is the sum of your entire path, which is 2.3 miles. So calculating displacement, you're going to look at the difference between where you started and where you ended out, and it's path independent. It doesn't matter where you traveled in between. So here's a quick little problem to look at. You leave a classroom and walk 10 meters north. You realize that you don't have your phone and turn around and retrace your steps. So you walk 3 meters south, find your phone. So the distance that you traveled is 10 meters plus 3 meters. It's the whole sum of every step you took. But the displacement is the difference between the two. So you went 10 meters forward, 3 meters backwards. So you're 7 meters north of where you originally started. And that's your displacement. Velocity is another quantity that you're probably familiar with. People interchange speed and velocity just like you think distance and displacement are the same, but they're not. Speed is going to be distance over time, and velocity is displacement over time. So you can see where that might make a difference. It is a vector. It's measured in meters per second, miles per hour, kilometers per hour. You'll see centimeters per second. For physics, we like to change everything into meters per second. And the symbol is going to be V with a little vector on top of it. And like I said, speed is distance over time. It is a scalar. It is measured in meters per second, miles per hour, just like velocity. And the symbol is going to be a V again. The difference is going to be for speed, it doesn't matter what direction you're going. And for velocity, you care about direction. So we'll look at the same problem that we did with our trip to Starbucks, and we're going to look at the difference between speed and velocity. So we're making the same trip, takes 7 minutes to get there. And your average speed is going to be the distance divided by the time, which is 19.2 miles per hour. And then the average velocity is the displacement divided by the time. So your average velocity is 11.7 miles per hour. And you can see that that's a much shorter length, took you the same amount of time as that very long distance length. So it makes sense that the velocity would be smaller than the speed. So instantaneous speed and velocity. This would be the speed or velocity at a single specific moment. With velocity, you want to know what the direction is. So you'd have 30 miles per hour north rather than just 30 miles per hour. And it's what you'd read right off the speedometer. You can also get it from a position time graph or a velocity time graph. You can also use calculus to arrive at it if you're given a function for the displacement. For our purposes, you'll either be given it, we won't calculate it, or you will find it from a graph. Acceleration is how fast the velocity is changing. So if an object is speeding up or slowing down, its velocity is changing over time. It's a vector, so the direction is going to matter. It's measured in meters per second squared. There's a lot of other units. We're going to focus on meters per second squared. And the symbol for this is the A with a vector over the top of it. So like I said, acceleration can be positive or negative, and that is going to be direction related. It's not speeding up or slowing down. Speeding up and slowing down have to do with a combination of the direction of the velocity and the direction of the acceleration. So if the velocity and acceleration are in the same direction, object is speeding up. And you can think of that if you're stepping on the gas and moving forward, you're speeding up. Now, velocity and acceleration are in the opposite directions, the object is slowing down. So if you're driving down the road at a speed and you hit the brakes, the car slows down. You're still moving forward, but the acceleration is negative. So that's deceleration. And once again, when we're talking about the instantaneous piece, it's measured at a specific time, and for our purposes, that'll come off of a graph. So here's a basic calculation for acceleration. You've got a ball rolling to the left with an initial velocity of 5 meters per second. It's going to come to a stop in 7 seconds. What's the acceleration of the ball? So little doodle real quick. It's got the arrow pointing to the right for velocity and acceleration, slowing it down. Using the equation, you've got the acceleration is equal to the final velocity minus the initial velocity, which is 0 meters per second minus 5 meters per second. You got to keep those straight. It's very important to keep what velocities are what straight, divided by 7 seconds. And you end up with the acceleration is negative 0.7 meters per second, or acceleration is 0.7, should be meters per second squared. So A is going from the right to the left. And you should get into the habit of using sketches to set up the problem and identify the given and unknown information. So here we have some graphs of motion, and they simply start off with position versus time, velocity versus time, or acceleration versus time. And they are related. You'll hear them called graph stacks sometimes. Think back to high school physics, you may have heard that. And so there's a relationship between each of these. If you start off with a position time graph, the velocity is the slope of the position time graph, and the acceleration is the slope of the velocity time graph. And if we focus in on the top one, we've got a stationary object. Its position never changes. The slope of that line is 0, so the velocity never changes. And the slope of the velocity line is 0, and so the acceleration is 0. And if you look at the middle one, the object changes position at a constant rate. It's a straight line. So the slope of that line gives us the velocity, which is going to be a constant value. And when we take the slope of that velocity value, since it's a horizontal line, the slope is 0, so the acceleration is 0. And on the bottom one, you have a graph of an object that is increasing the distance. So its position is getting farther and farther and farther apart every time interval. So it's getting faster, and if you take take a bunch of different slopes at that line, you're going to end up with increasing values of velocity. Calculus here helps, but just trust me on this. And when you take the slope of the velocity, it's going to be a nice constant value. So those are graphs of motion. And you can tell what something's doing based on its graph of motion. And so here we have a position time graph of some object, it doesn't matter what it is, and for the first 10 seconds, the object moved forward 60 meters, and I used the slope and found that it had a constant velocity of 6 meters per second. And then for 5 seconds, it's sitting still. Didn't move anywhere, has no velocity. And then for the next 25 seconds, it actually goes backwards for 100 meters, and it has a constant velocity of -4 meters per second. And then those last 10 seconds, it moved forward at a constant velocity of 20 meters per second, and it covered 20 meters. So earlier I said that you could find the instantaneous velocity from a graph of motion. So here we go. So here's that same graph of motion, and I want to know what the instantaneous velocity is at 25 seconds. And so you find the 25-second point, and it's on that nice little downward pointing line. And so we're going to find the slope of the line, and that's going to give us the instantaneous velocity. Use change in y over change in x, and you get -4 meters per second. Alrighty, bye-bye.